Recording is rolling. It is Wednesday, August 20th. So I'm just going through these slides yesterday. I didn't quite finish it, so I've got a few more we're gonna go through there. You guys, there's trigonometry page. So once I was allowed, the other side is these triangles. Uh, let's bump the due date back to Friday. Yeah, I'm gonna bump everything pretty much back a day on this. So I want to get started on this last half of class today. Okay, give you guys more time for that. And what I'm trying to work towards is getting towards actual linear motion. Have you guys roll these Hot Wheels cars down the incline? Okay, so at some point I'm going to clear all those lab tables back there. You guys see all those projects back in lab tables. Some guys left Geneva drives or some. Well, my class are doing like building abacus, so gonna pop some stuff. So yeah, something back there, and you want to take it home, then take it home too. Okay, yeah. So yeah, I'm also looking at this quiz date. I'm gonna bump that back to also next Friday. Got all going on. So I'm trying to shift everything back and yeah, go with it. So it's all gonna work with me now. Okay. Friday, there's a pep rally. Friday, there's a pep rally. So we're gonna be on this pep rally schedule. So it looks like every class is gonna be shaved a few minutes, and then a pep rally starts around 1:56. So look for that on Friday. Guys, there is an infrastructure. Oh, whoops, do I not have that written? Yeah, okay, okay. Guys, today during period two, there's an infrastructure test. So have your laptop ready to go, period two. I think they want everybody on at the same time to make sure the system doesn't crash. In preparation for if you're in 9th and 10th grade, you'll be taking a fast test next week. Okay, so any questions about agenda stuff? You guys good? Good there? All right, so going through these slides from yesterday. Here's one of the slides I was looking at. I was telling you guys about these measuring tools, and one of them, I did not have at the time, but I do now. It's this one right here. You guys see the one that says motion detector for displacement, velocity, acceleration. Now, displacement is like how far have you moved from some initial place, which you can measure in, say, meters or centimeters for that matter, or kilometers, right? Velocity, guys, is velocity like how fast, like a speed? Right? But it's also direction. Sometimes direction is applied, sometimes it's specified, right? But you can quantify that in meters per second and also some angle, right? That's one reason we're doing some trigonometry is to work with the protractor and some angles too, right? But this could measure like a speed, how fast. And guys, what is acceleration?
Increasing speed.
Yeah, increasing speed, right? So if you're in a car and you're slamming on the gas pedal and speeding up, can you feel that inside the car? Right? What if you slam the brake and you come to a stop? Can you feel that too? Is that also a type of acceleration? Yeah, yeah. Sometimes they say deceleration. Okay, in this class we're going to call it like a negative acceleration. That's what we'll call it. Well, we'll assign a like sign to it, like plus minus. Okay. Oh, wait, this tool right here. Looks like it's got this little USB. No, I have a whole box of these, so I will put these in your hands for this upcoming lab. And if you want to try to use it, you can. I always have trouble getting this to work, but you might get it to work. So if you want to try it out, you can plug this into your laptop, and if the car's headed straight towards it or straight away from it, you should be able to pull up the program, and it should like give you graphs for all these readings. So that's optional if you want that. Put that in your hands, and then AP knows what a motion detector is, so that could be a possible tool you could write about on an AP exam. Okay. All right, so I want to fill in that detail. All right, let's get back towards about where we were yesterday. All right, so looking at this one here. Okay. So this was towards the end of class. I was getting to this one, scaling. I want to round back and revisit this one. Yes, guys, this is a big important concept that you're guys going to see all over this class in physics. If you scale from, you guys see this little tiny box and this big crate that's a linear factor of three times as wide, 3 times as deep, 3 times as tall. Right? I just like blew it up proportionally. Okay? But different properties change at different rates. Okay? Anything you do with linear is okay, whatever the linear scale factor is, 3 to the 1. Okay? Anything to do with area, if I want to paint it, is not like an area concept or a shadow. Okay? That's a squared factor. 3 squared is 9. Anything to do with volume, mass occupies volume, weight is proportional to mass. Okay? Is well, that's like a three-dimensional concept, isn't it? Okay, so linear scale factors. Hey, now I'm showing a cube here because what if this wasn't a nice cube shape? What if it was? Oh, here, draw that. What if I have like a little baby elephant, okay, and I have like a huge elephant that's like 3 times as tall. It's like okay. So what if this height is like h, and this guy's like like 3H, like 3H times height, like 10 meters and 30 meters or something. Right? You guys get that? Okay. So this is clearly not a nice box shape. It's just some weird shape. Okay. Do these scaling up factors still apply? But like here, suppose you put the little baby elephant on a scale, okay, and he weighs some amount, and you put the big elephant that's 3 times as tall on a scale. Okay. Approximately how much should the big elephant weigh compared to the little tiny elephant? Who says 27 times? Who else says 27 times as much? 27 times as much? Yeah, yeah. Because 3 times as tall. Don't forget 3 times as wide and 3 times back into the paper too, right? Okay. And then, okay, so it's going to be 27 times the volume, but also weigh 20 times. Okay. Wait, 27 times as much? All right. I think the last things you guys saw yesterday, I was having you guys solve these algebra puzzles. I got a couple of these. Okay, so they got all these algebra steps. You guys feel comfortable solving these algebra puzzles? Right? Because you're going to use pretty much almost every day in this class. This is going to be incorporated to like a bunch of equations we're going to do. Okay? Now, there are different types of graphical relationships. This is a really common one. This is a linear relationship. Okay? So like if you say like double this x factor, then this y factor might also change by factor two. Okay? Actually, that would strictly be true if it went through the origin. Okay? If this goes through the origin, oftentimes it's called a direct relationship. So if I double one variable, then another variable also doubles. Okay? Oh, I know that's a really generic thing to talk about, like generic variables. So how about when your car is going down the incline, cars say going down the incline, okay? What variables could you maybe keep track of? What's one variable do you think might affect the motion of the car possibly? Huh? Yeah, okay, yeah, the angle, right? The angle, right? So like if I double the angle or something, now angles are a little bit tricky because there's probably a sine or a cosine involved, right? So we're not going to mess with that one so much this week. Okay, what's another factor? But that could be a factor that could affect it, right? And we'll round back to that in a few weeks. What's another factor maybe that you want to test for?
Like the material of the road?
Um, okay, yeah, maybe. Since the car's going to be rolling, then it turns out that if there's a little friction or a lot of friction or not very, that, yeah. Now in the future, if it's sliding, if you turn it upside down, it's sliding. That would definitely be something we want to test for. We'll definitely look at the future. Now rolling though, yeah, won't really worry about as much. Did you say like the mass of the car or the weight of the car? Yeah. Okay. Now that'd be something you want to test for. Yeah, because maybe if you start taking lab weights to it, right, that could change it. How about how far does it roll and how much time? Do you think there's some like guys, if it rolls double the distance, do you think that's going to take double the time? Or more time but more than double, or more time but not quite double? Huh, huh, right? Or what about what other variable do I have here? Oh, speed. Okay. I was showing you guys this motion detector, but what I know for sure works a lot better is the speed gate. So guys, when the car goes through the speed gate, zoom, okay, what's the relationship between how much time it's been rolling for and the speed? Like if it's been rolling for double the time, is that double the speed?
No.
Maybe, maybe not. Uh, if it's been rolling for double the distance, does that build up to double the speed? Huh. Huh. Maybe one of those works and one of those doesn't. Okay. So if you thought there was like a double-double relationship, then that would work out to a direct relationship if this was like going through the origin. Okay. Could you guys imagine that? Okay. And if there's an intercept, sometimes that has some physical interpretation too. Okay. So if I ever just rattle off y equals mx plus b, we're referring to something like this. Okay. Now, what shape graphs are you going to see in this class? Pretty much just this list right here. Do you guys see these 6 graphs? Okay. Now, these are not all the graphs around the world, obviously. Okay. But for an AP Physics 1 class, I think this is all you're ever really going to run into. And there might be like an oddball graph that is not on this list, but it's pretty much. Okay. So let's go through these. Okay. Because this is like, if you know these relationships, then pretty much just look for these. Okay. I think it's all you're going to need in this upcoming lab with the Hot Wheels cars. So one might be no relationship at all. Do you guys see like if you increase this variable x, whatever this is, x could stand for, oh, I don't know, mass, distance, time, speed, or whatever. You're directly changing something. Okay. And then whatever variable might possibly respond to that, turns out it doesn't care. Okay. Do you guys see that like if I double x, y says, I don't care, I'm just doing the same thing I'm doing. Huh. You guys see that? You see that? Okay. Now I threw these little dots here because your actual lab data, there's oftentimes some error measuring, like especially with the stopwatch, right, trying to measure like how much, whatever. Okay. So it's really common for not to make like a perfectly clean graph that like, there's a little scatter plot, you have to draw a line of best fit, zip, right? And it tells you something about the overall trend. Okay, that's you guys see that's true for all these. I drew dots that kind of scattered around, but there's some overall trend you can zip put a line of dust fit through. Right. Oh, here's your linear relationship or direct relationship that goes through the origin. Okay, that's to say if you double the x, you're going to double the y. Okay, so if you triple the x, does that also triple the y? Yeah, yeah. Again, x and y could stand for like any of those variables we're talking about, like mass, distance, time, speed. How about an inverse relationship? Okay, so if you increase some variable x, some variable y is going to decrease as a result. Huh? Inverse relationship. Okay, I'll give you guys an example. Real classic example in physics is Newton's second law of motion. What's the relationship between mass and acceleration for a given force? Okay, so say I got these two objects. Is this one little tiny mass? Little tiny mass? Very little inertia. This one's a big mass. There's a lot of inertia, a lot of resistance to change in motion. What if I put the same force on both these guys? The same force. How much does either get like change its motion? I'll call that acceleration. Let's try this guy. Ugh, it was hard to knock that guy down. Let's put the same force on this guy. I'm gonna fly across the room. So what I just showed you guys is that here's a big mass. Here's a little tiny mass. The big mass hardly moved at all. The little mass, that was a huge acceleration. So if it did an acceleration as a function of mass, it would actually make a curve that looks just like that. Okay. How about guys, you guys see parabolic relationships all over the place. And if I had a negative half of the x-axis, wouldn't it make a nice parabola looking, like a parabola? Okay. How about this? Guys, I throw something straight up in the air. What is its height as a function of time? Doesn't it go up and then kind of slows down and then it comes back down faster? So if you made height as a function of time, do you think it would be this shape graph just like upside down? Like an upside down looking parabola? Right? So look for parabolas all over the place in this class. You'll see a bunch of them. Okay? Okay. Something to do with like y equals x squared. No, it's a very simple example version of that. How about a root relationship? Like y equals the square root of x. Doesn't that like hook down kind of like this? Right? Now, if one variable grows, the other also grows forever, but maybe at a slower rate. Right? Guys, look how I wrote this. X to the power of 1/2. Is that the same thing as the square root of x? Let's see if it is. See if I got a calculator right here. Okay, like if I did the square root of 16, guys, square root of 16 is what? 4, right? Okay. What if I do it this way? What if I do 16 and I hit the caret key, 0.5? Isn't that 16 to the power of 0.5? Is that the same thing? Yeah, sure is. Sure is. Right? Sometimes I'll do that. You take a square root, I'll just do power of 0.5. Like if I do answer of 0.5, I'll do the square root of 4. The square root of 4 is what? 2 point. Right, so it's not good. Right, and this last category we probably won't get to till like January, maybe I'm thinking, like sinusoidal. So does this look like okay, y equals sine x where it oscillates back and forth? Okay. A lot of times this involves springs or pendulums. That's your main two categories for this, like some kind of oscillating motion, a spring or a pendulum. Okay. Right. So look for those in this class, and if you know these, then yeah, you'd be able to pretty much draw any graph they want. Probably ask for on the AP exam. All right. Any questions about graphs? Graphs. Okay, you guys go with graphs? All right. So speaking of parabolas, that's gonna link to this next one. Does this look familiar? Quadratic formula? Quadratic formula? Okay. In fact, that example I just gave you, if you toss something straight up and it comes straight back down, if you, that's exactly what this graph is showing. Look, height in meters, like variable unit, height in meters as a function of time in seconds. So say time's ticking along and somebody throws something straight up, like a ball straight up in the air. Now time is ticking forward, so maybe you threw it straight up and it comes straight back down, just goes straight up, straight down. But as a function of time, height as a function of time is going to create this parabola looking shape, right? Now in the old textbook I was using up till last year, I know there was a question. I think your guys too. Did you guys notice that I did post some linear motion puzzles on Google Classroom? Right, so trying to get those out ahead of time, a few days ahead of time. Right, so get those to you guys eventually. There's a question that involves like either throwing a ball in the air or a set of keys up in the air, and then like somebody catches them like a few floors above, something like that. Right, and the question is like, what time would you catch the keys? Or that could be one question, right? I throw something in the air, and then what time does somebody catch it, like in the third floor windows? Okay, something like that. Okay. And do you guys see that there's actually going to be two answers to that? Because suppose you caught it like right here, right? So you could catch the keys or the ball on the way up, or they could overshoot and come back down. You could catch them on the way back down. There's two possible times at that particular elevation. You guys see that? Right? So there would be two solutions, two potential solutions. Okay. Guys, how many solutions do you get out of the quadratic formula? Yeah, usually two, right? Right. That's what's plus or minus, right? Or maybe zero if this guy's like way up here that it never reaches them at all, right? Or maybe one if he's right at the very peak, right? But yeah, oftentimes you get two, right? So that one's a good one to know. I think AP does give this to you anyway. Let me check. Let's double check. You guys remember this AP formula page? Okay. Is the quadratic equation on here? I think it used to be. No, is it not? Maybe it doesn't. Well, I thought it was. Never mind. Maybe I'm wrong about that. Right. But that might not be a bad idea to memorize that, maybe. Right? That could help you out. Right. Oh, some geometry. Do you guys know circles and spheres? Let's start with circles. Let's do okay, circumference of a circle. How long it takes to walk around a circle? What's a good formula for that? Ooh.
Is there radius?
Okay, guys, I'm hearing a couple of candidates. I'm hearing a 2 pi r being thrown out there, and I'm hearing a pi r squared being thrown out there.
That area, that's the first one.
Okay, yeah, guys, let's figure this out critically. Let's do some critical thinking here. If I have a circle, right? Okay, because guys, if you can figure out how formulas work, then you'll never forget it again. Let's think about this. Okay. I might have you guys do this activity one day. But what if this could be the radius, right? Is that the radius? Right. What if you cut a length of string, right? You start to wrap that string around, right? Do you guys think that one radius worth of string might get you to probably about right there? Probably right there. Okay. By the way, all right, here's a little side trivia question. What is this angle that where this r worth of string wraps right around the circle? What is that angle right there? What is it in radians? How many radians is that?
Hopefully a single.
Yeah, one. That's 1 radian. That's what 1 radian is. That's it. That's 1 radian, right?
That's all.
Yeah. Does anybody know how many degrees that is approximately? Close. It's about 57 degrees. It's about 57 degrees. Not exactly, but pretty close. Okay. Yeah, that's 1 radian. Right. All right. So let's keep going. Let's do another string gets you to about right there. Another string gets you to probably right about there. Right. And we're not quite halfway around yet. So that's 1, 2, 3 radius worth of strings, isn't it? You see that? 1, 2, 3. Okay. And you keep going. There's 4 gets you to about there. 5 gets you to about here. 6 gets you to about here. And there's a little bit left over. Okay. Ooh, okay. Something to do with pi, right? Something to do with pi? How many strings do I have? 1, 2, 3, 4, 5, 6. And there's a little gap left over. If I wanted to finish the gap, that's altogether how many? 6 point what? 6.28. Aha. Is that like 2 pi? Is that like 2 pi? Oh, look at theirs. Look at theirs. So go all the way around the circle. You need 2 pi times the radius, don't you? Yeah, that's circumference. Circumference equals 2 pi r. Right. Now, this should ring a bell though. The pi r squared. What does that refer to? Area? Right. Let's do something different with the circle. Let's do this. Let's do this. Right. Say you have this radius r, right? Okay. What if I square this off and make a physical square right here? Okay. Could the area of the square I'm hashing in right now, wouldn't that be r squared? Isn't that the area of that square? Right. And let's say this is maybe some amount of paint or something, right? And you want to like completely fill the circle. You want to paint the face of the circle. Okay. So we're talking about areas, right? Okay. How many of these squares exactly does it take to fill the circle? 4? Wait a minute. If I did 4, let's throw 4 on the board. Right. That would cover the circle, but then I would have all this periphery hanging. Like I could cut off this and this and this and this. So it'd be less than 4, right?
3.
3? You guys think 3? Okay. Let's look at 3. Because if I did 3, it'd be these 3 right here. Now, guys, could I cut off this corner and this corner and this corner and probably fill most of this last space right here? But okay, but it turns out it'd still be a little bit short. So it's not exactly 3.
3.14.
3.14. That's what this is right here. Look at that. That's area is pi r squared. You see that? Right. So here's another way to think of this. is that circumference is how far you walked in meters, and radius is also a length in meters, isn't it? Because you take meters and scale it up by some number, it's still meters. And an area, can an area be in square meters? Like square feet, square meters? Okay. And if you take radius in meters and you square that, that also gives you square meters. Right? Right? You see how units work too? Right? Like straight from a math class, you have to like memorize these formulas probably, and then you figure, I forget which one's which. But if you're in a physics class and you know how units work, then you'll never forget it. Because you know, oh, well, circumference is proportional to just how far radius. In area, you have to square that radius. You have to get like an area. Okay? Okay. All right. So there you go. There's circles. There's circles. All right. You guys did a nice job on circles. We got circumference is 2 pi r, and we got area is pi r squared. So you guys can know those, right? How about spheres? We might come across surface area, maybe. I don't know. We'll see. How much paint does it take to paint the surface of a sphere? Does anybody know? It's like here. I'll take it. It's like 4 pi r squared. Right. So that's fun trivia. Right. Now this last one, volume of sphere. I think will come up in this class because we're talking about like the volume of a planet. Okay. Well, a planet is pretty close to a sphere, right? Right. Yeah. So yeah, it's 4/3 pi radius. And guys, if you need a volume, that'd be radius to the power of what? 3. Aha. Okay. So similar idea. If an area has something to do with radius squared, a volume has to be radius cubed. Okay. 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 All right. So there's let's run down to that. How many guys are in calculus? Who's in calculus? Oh, a lot of you guys. Okay. Here, I'll throw a little calculus tidbit, you guys, and well, maybe this will make sense. I don't know. Okay. Let's say you painted the surface of the sphere, and you put on another coat of paint, another coat of paint, another coat of paint. They're really thin coats of paint, but does that overall make the sphere a little bit bigger, bigger, bigger? Right. So over time, you're going to grow the sphere. Like every coat of paint, maybe like 1,000 coats of paint, it's getting pretty big now. Okay. Okay. So, every time you apply coat paint, what you do is you're changing the volume of the sphere by a tiny rate at a time. It's like a rate change in the sphere. Okay. That's what calculus is, like in a nutshell. Calculus is about rates of change, about rates of change. Okay. Okay. And does anybody know how to take a derivative? Okay, you'll learn this in a here. I'm gonna spoil this for your math teacher. Sorry, math teacher. Okay, you guys watch this trick. So a way to take a rate change is you guys see r to the power 3. So radius is being like a variable, kind of like an x variable, right? Okay, take that 3, bring it down in front. Guys, what is 4/3 times 3? 4/3 times 3. The 3's cancel, and I just get 4, right? Just get 4, right? And then you subtract 1 from this power. Guys, what's 3 minus 1? 2, right? And that would be 4 pi r squared, right? And what that tells you, that's the rate change of its volume, which would be the surface area with respect to radius, wouldn't it? It's exactly this right here. Is that? All right. So I don't know if that makes sense or not, but okay. Okay. And then now we did this the other day. So you guys know this. Okay. And now we're back to the finally. Woo, we finally made it back. We made it. All right, you guys ready to put it back to trigonometry? All right, so you guys got this out. We're finally back here. We made it, guys. All right, so again here. Now, everybody has a protractor in their hand. So just to remind you guys, you're making 5 measurements and 6 calculations. So you're measuring the 3 sides of every triangle. You're going to measure the 2 angles using the protractor. That's what alpha and beta are. Okay. And then from that, above the column A where I wrote calculate, you just apply the formula that we wrote the other day. Right. And remember that you're getting different perspectives on, for example, this, let's say this side B right here. You guys see the side B? Okay. You could directly measure it with a ruler. Here's my ruler right here. Okay. You could directly measure the side B. Okay. And it'd be so many centimeters long. Or you could do C, the hypotenuse, times what? Also gives you side B. C times what? Let's say you're playing off this alpha. Sine alpha. Guys, get really comfortable with that motion right there. You're going to do this probably 1,000 times in this class. C times sine alpha also gives you side B. Or what if you're playing off this angle beta? C times what? What's adjacent? Cosine. C times cosine beta also gives you side B. Right? And then if you knew what if you didn't know the angles exactly, but you knew it's a right triangle and you know side C and side A because you also measured side A. Okay. Could you apply Pythagorean theorem, do a little algebraic rearrangement, and also solve side B using the Pythagorean theorem? Right. So there's 4 different perspectives on side B, and that's these last 4 columns here. I'm just reminding you guys from the other day. Do you guys remember all that? Right, you guys remember that? Right. Now let's look at the backside of this page. Okay. So you can use this as your reference triangle, and there's 10 different triangles here. They're a little bit different angles, but they're all going to be right triangles. You know what I wish I did? Okay. All right. Did you guys see how the sides of the triangle are actually arrows, like vector arrows? Okay. So the side Z, let's call it like the original vector arrow. That's just a solid arrow. Maybe you're moving up and to the right. Maybe you're pushing up and to the right. Maybe you have some velocity up and to the right. There are lots of types of vectors. Vector has a magnitude, like how much, but also an angle. Hence this alpha down here and this beta. Okay. But then you want to say, well, how much up and how much to the right? Right. Now we're going to break out some sine and cosine. Right. Now what I should have done, this is a terrible mistake on my part, is I should have not drawn these 2 vectors solid. I should have dashed them because that's how you apply this in physics almost all the time. So go ahead and do this with me just to get the practice of it. See, I'm actually dashing, dash, dash, dash. The same thing with y. So side x and side y should actually be dashed, okay? Because those are vector components. So like if you're moving northeast, like how much north and how much east, right? But if you make them solid, then what you're communicating to whoever's looking at your diagram is that you're sort of like double counting the vectors. Okay, so make sure to dash those vectors. Okay, you see that? Okay.
Wait, is this and this that?
Right. So the diagonal one is solid. Side Z is a solid vector, solid arrow vector. And then X and Y are both dashed. No, they're both arrows still. They still have the arrowheads on them, but they're dashed. You guys see how side X and Y are dashed? It says. Right. Right. Now, here, maybe I'll do like a few of these with you guys, and then I think you'll be able to get from there. So number 1, I think is real straightforward. You guys see number 1 is, let's say you walked 125 meters. You guys see 125 meters? 30 degrees north of east. Isn't that what alpha is? It's like north of east. Okay? Maybe give a direction. Okay? If you know that, and you know this is a right triangle, that's all you need to figure out everything else about this triangle. Yep.
You have 125 70.
Oh, yeah. Guys, there are a bunch of different versions of this. So we all have different numbers, but you should have something for Z and something for alpha. You guys got? Okay. But maybe you have different numbers than I have. Yeah, I forgot about that too. Oops. Okay. So, let's do some math here. Because you guys know this is an abstraction, so don't actually use your protractor for this. But guys, if alpha is 30 degrees, ideally what should beta be?
60.
How'd you know it was 60?
30 plus 90.
Yeah, because these 2 are complementary angles. They have to add up to 90, right? And of course, if you throw in the right angle, it brings it to 180 for the whole triangle, right? Okay. A flat triangle. How can you, what's one way you can get x? I can think of a couple ways. What's one way?
V times cosine alpha.
That'll work. Z times cosine of alpha. Right? And since you know Z, because I gave it to you, my paper says 125 meters, and you know alpha, which I also gave you, and mine is 30 degrees. Okay. Yeah, that'll give you side x. Okay, so you can pop that in your calculator to get that. Okay. What about side y?
Sine alpha.
Yeah, you could use Z times sine of alpha. That'll definitely get it for you. What else could you have done? Z times what? Cosine beta? And I heard somebody say Pythagorean theorem. Okay. Now, if you do Pythagorean theorem, would you have to do Z squared and then minus, don't say plus, but minus x squared and then take the square root of that? Or you could derive that from scratch if you weren't sure where that comes from, right? Okay. Oh, how about let's do, okay, so I did number 1 with you guys. Let's do number 7 and how about number oh yeah. Oh yeah, you should be in decimals.
Okay.
Yeah. Right. How about?
How much?
Okay, yeah, we gotta finish that then. So back to number 125 times cosine of alpha was 30 degrees. Okay. So on my paper, I'm getting 108.2531755. Okay. Now, guys, if you're talking about how far you walked in meters, right? Think about what this means in context of meters. 108 meters, or how about 108 meters and then 20 centimeters is like 2/3 of the stroller. Okay. Or how about this? Like 25, that would be 108 meters plus 25 centimeters. Or that. The next digit, guys, that 3 there, that 3 represents how many what? Millimeters. Millimeters. Guys, if you're walking across the field, 125 meters, isn't that like going across a football field? Do you think at that point you care about, and I also went an extra 3 millimeters? Do you care about that at that point?
Alright.
That's kind of ridiculous, isn't it? Yeah. So at some point you get a cuff. Now in this class, a good rule of thumb is if you have 3 digits, that's usually fine. Three or 4. Now, if it's a middle step that you need to carry over to more calculations, maybe keep a few spare decimals. Okay. That's your final answer. Like if I wrote 108.25, that'd be plenty enough. In fact, if I just went 108.3, I could do 108.3. That's probably all I do. 108.3. Here's okay. Let me try the signed version right here. 62.5. Yeah, just keep that. 62.5. Okay. Now, different classes. I think in a chemistry class, they're like really sticklers about significant figures, and there's like strict rules, like however many digits you start with is all you're allowed to have in your answer at the end, sort of. That's kind of a basic rule of thumb, right? But in physics, in AP physics, they're not sticklers at all. So if you only have 2 digits to work with and you write 3, then they'll accept that. So that's fine. Okay. All right, let's do what did I say? 7 to 9. Let's do 7 to 9. So, now number 7, I have 60 newtons up and 80 newtons across. You guys see 60 up and 80 across? You guys see that? Okay. All right. So, what should I do? Because what's one? Ooh. Yeah. I could get this angle by doing, you said inverse tan? Inverse tan? Right? In fact, I have the 2 legs, so it would be specifically inverse tan. Like, I can't really touch sine and cosine yet. Okay. But yeah, this angle alpha right here could be inverse tan of, and what would be y over x. Is that right? Okay. So for me, that would be 60 over 80. Is that true? Okay. So 60 over 80. Okay. Oh, and also I have units. I have newtons. So that's just how hard am I pushing it? Oh, yeah.
I got 36.9.
Ooh. Yeah, I think that sounds right. 36.9 degrees.
Yeah.
Right? 36.9 degrees. Where have you guys seen that number recently? 345 triangle. Is this gonna be a 345 triangle?
Yeah. Well, it's 80.
It's so fun.
What's the ratio of 60 over 80? 3 to 4. And if that's true, then what does Z have to be?
100.
100 newtons. Yeah, and you can do Pythagorean theorem, but it would have to tell you that, wouldn't it? It's a 3, 4, 5 triangle. Okay. Here, guys, let's do some Pythagorean theorem. What's the square root of 60 squared plus 80 squared? All right, 60 squared plus 80 squared. It's got to be 100. Exactly. It is. Yeah, because it's a 3, 4, 5 proportion, right?
That is not.
Just 3, 4, 5 scaled up by a factor of what, 20? I think? Right. How about this? For beta, let me do something tricky here. For beta, could I also apply an inverse tan, but just swap what's opposite, what's adjacent, like do x over y? Because what's opposite and adjacent is opposite for alpha and beta, right? Can I just swap that? Let's see if that works. What is inverse tan of not 60 over 80, but 80 over 60?
50, 31.1.
Yeah, you guys getting that sounds right. 53.1 degrees, right?
Yeah.
And let's say this. If you add alpha and beta, what do you get? 90 degrees. Oh yeah. That's another way you could have figured it out too. Okay. You guys get what's that?
You really solve for one of these.
Right. Yeah. Guys, once you solve one of these, then now lots of doors open up and there's lots of pass through the forest to figure out how to solve everything else, right? There's more than one way to go about these. Okay. All right, let's do number 9, and I'll give you guys the rest of the class time to work on these. All right, so number 9. Oh, so here I have one of the legs and the hypotenuse. So here, let's chase down y first. Let's chase down y. So if you know z and you know x and you want to know y, it's a right triangle, but right. What can you use? Yeah, Pythagorean theorem. Right. Here, I'll start from the beginning, just in case anybody needs to see it from the beginning. Right. So that could definitely be true, right? That's just straight Pythagorean theorem. Okay. Now let's do some algebra. So I can subtract off the x squared. Y squared equals z squared minus x squared. And then take the square root. So y equals oh, is that z minus x? Is that what that is? Z minus x?
Yeah.
Huh? Huh? Square root of z squared minus x squared. Okay, that's different. That's different. Okay. Now, guys, if I was multiplying here, I could get rid of the squares. The square and the square root would cancel. But if you're adding and subtracting, it doesn't cancel. Okay. Okay. So you guys can do that. Here, I have 37 versus 31 kilonewtons, it looks like. So if I do square root of 37 squared minus 31 squared, okay, I'm getting 20.199, call that 20.2 kilonewtons. Okay. Okay. How can I get let's say alpha, and let's say I'm just playing off the x and the z. Let's do that. Let's get this alpha right here, just playing off x and z. Inverse cosine, exactly. Yeah, so I'm doing an inverse trig, but I'm going to play off the cosine. So that'd be inverse cosine and be x over z, like that. Yeah. So inverse cosine, and then, okay. Now my x and z are 31 and 37, so 31, 37. Okay, so inverse cosine, 31 and 37. That's giving me 33.1 degrees. So 33.1 degrees. Okay. And then how do you guys want to get beta?
Subtract 33.1 from 90. It's 59.
That'll work. Yeah, I could just do 90 minus that. Yeah, and get 56.9 degrees. Okay. And if you wanted to double check your work, you could use a different method. And yeah, like an inverse tan of the legs or something. Okay. All right. So any questions on any of this stuff? Right, so you guys have these 10 puzzles on the side. You guys have this trig lab on the side. I'm going to treat this as two different assignments. I've got two different assignments in the grade book. And okay, so let's have the due date for this be Friday, so you have an extra day for that if you need it. And tomorrow, I think I'll check on you guys, see how you guys are doing on this, and try to get you guys started on this next lab, or at least start thinking about it. Right, so that's kind of my plan. All right, so go ahead and make the best use of these last about 10 minutes we have, and I'll walk around and help you guys out.